Hello everyone. I hope you all are safe at home. So till now we have completed around 20 lectures. After the recording is completed, I will upload it so that you can access and go through the lectures. So what I will do, I will not make a full length video of the whole lectures, but I will split it into different parts, so that you can very easily download if you want and see the lecture. So till now what we have discussed, so this is lecture number 21 of solidification processing. So we have been discussing about nucleation, homogeneous nucleation. We have discussed, we have derived different relationships. After that we also have discussed the heterogeneous nucleation and derived the different relationships, like what is the critical size, what is the critical free energy required for the formation of phase. So today I will very quickly go through all these details what we have discussed. So this is for the sake of completion of this video lecture, so that you can start from this and follow the remaining lectures. So when solidification happens, why essentially solidification happens? So solidification happens because the liquid moves to solid in order to reduce the free energy. So solidification occurs because the liquid wants to achieve a more stable state, which is solid. Thereby it reduces the free energy. So if we draw the free energy versus temperature diagram, say G is the free energy. Say this is we can consider it to be molar free energy versus temperature. So we know that free energy versus temperature line. So if we have we plot for solid and liquid together, say the liquid will be, so this is the temperature at which free energy of solid and liquid both are same. So now the question is, which one is solid and which one is liquid? So at temperature, so this is the melting temperature at which both the liquid and solid phase just coexist. So the free energy of both the liquid and solid will be same. So this is the melting temperature, we can say. Now at temperature above melting temperature, the liquid state is stable. So the liquid will be have lower free energy and the solid will be having higher free energy for temperature above melting temperature. Now if you consider a temperature below melting point, the liquid is having a higher free energy, so the liquid will not be a favorable state. So the liquid will try to convert into a solid, and the solid has lower free energy. So suppose if the transformation is taking place at this temperature, this T. So this drop, this is the amount of drop in the free energy that we call it, say delta G volumetric free energy. So this is like if you have a liquid and a solid nucleus is formed or a cluster is formed. So you have n number of atoms in the liquid, and when you drop the liquid, say very close to melting point, there will be lot of thermal agitations and large number of clusters will be formed. The clusters will have variable size. We will discuss this thing. We have discussed how the free energy changes. Free energy change depends on the cluster size. So, but anyway, so what happens when the cluster is formed? This is the small. It is a collection of some number of atoms. So this phase is stable. That's why the liquid is converting into solid. This is a solid cluster form. Now what is the, why it is happening? Because the system wants to reduce the free energy. So that is the driving force actually. So this is the driving force for nucleation, or you can call it more, to be more specific, this is nothing but the molar driving force for nucleation. So this is the molar driving force for nucleation. Now when solidification occurs, if you see, like this is the formation of a small cluster. So this is how it will start. So when it happens, free energy is changing, but it is not the only negative change in free energy, because you are creating a surface. So if you write down the total change in free energy, there will be negative term, there will be positive term also. Because this negative term is coming from this phase change, liquid to solid, associated with this volume. And the positive term is coming from the surface, that is the surface being created. So this is the free energy this part is the free energy change due to phase transformation. So this will be proportional to the amount, or say volume of phase that is transformed, and this will be proportional to the surface that is formed. So what happened? These two terms we have already discussed that. So delta G, this term can be written as if we consider a spherical, so sphere being sphere of radius r is formed. So we can write volume will be 4 by 3 pi r cube. So this there is a negative term. Then delta G, this is the driving force. That is this is driving force because this system wants to reduce this much of free energy by forming the solid. And surface free energy, because it is creating the surface, some amount of energy, positive change in energy will be there because of the formation of the surface. So that can be, we can write, if it is a sphere, 4 pi r square gamma SL. So this is also per unit area surface energy. This is per unit volume free energy. So now if you see, we have already discussed. So the moment you create a surface, there is a negative change because of the phase change, there is a positive change. So this positive change, the system will ultimately the system will try to reduce the free energy, but because the surface is being formed, the free energy is increasing. So this is a kind of resistance. So the surface free energy which is being created or added to the system, that is a resistance to the solidification. So until and unless this becomes greater than this term, this volumetric free energy greater than say G volumetric, if it is until and unless it is greater than say surface free energy, the solidification will not occur. That means in total the free energy has to be, delta G has to be negative. Then only the solidification will continue, the nucleus will grow. So now you see, we have already plotted this curve, delta G versus R. You see, this is the function of R. In cube terms, you have a square term. So square term is positive. So this will grow like this. Negative term, it will grow like this. So initially what will happen, the moment you create a surface, the free energy, so the overall change will be something like that. So initially this is the surface free energy. Initially this will dominate the overall change in free energy. That is the energy of formation. If you want to create a surface, so delta G can be defined as energy, or to be, say, it gives free energy of formation. We can write it, gives free energy of formation. So initially it will be dominated, the overall behavior will be dominated by the surface free energy. Actually, when you have a very small surface, the surface by volume ratio is quite high. So the surface, the contribution of the surface energy becomes the dominating one. So that is why it is positive. And then after some time the cube term, this is the volume, say this term is the volumetric free energy. So after some time this cube term will dominate, and this is, so as you can see, there is a maximum to this overall behavior. This maxima is called a critical free energy change, and the corresponding size at which this is the size of the cluster at which this maxima occurs, that is called the critical size of the cluster. That means if you have a cluster on this size, little bit bigger than this size, the free energy, it will try to increase, the cluster will try to become bigger in order to reduce the free energy. So that is also a favorable condition, and the transformation will continue. Liquid will be transformed into solid. But if your say cluster size is smaller than R star, there can be n number of clusters of different sizes because of thermal agitations in the liquid when you drop the temperature. Now if the size is little bit smaller than the, say any size smaller than the R star critical size, what will happen, in order to reduce the free energy, the cluster has to reduce the size. That means it will get dissolved into the liquid again. So this will not continue the solidification. So in order to study the kinetics related to the nucleation, we need to identify this term and this term. So then only we can analyze the solidification in details. So the clusters which has this size greater than R star is called nucleus or nuclei. If it is one, then nucleus. So letter there, we call it nuclei. Because there will be large number of clusters having size greater than R star. So the sizes of the clusters having a size less than R star we will call M. So you can understand now, to continue the solidification you have to, if you want the solidification to continue, I mean the liquid, if you want the liquid to transform into solid, the cluster size has to be bigger than this. So for the cluster to be bigger than this, or the cluster to be called a nucleus, it has to overcome this kind of energy barrier. It has to form initially and then it will become bigger. But for that it has to overcome this barrier. Then only it can reduce. So initially the surface energy, initially the total free energy change will increase. So this is called, that is why delta G star is called the activation barrier. You see, this delta G we call it driving force, and this is the activation barrier. And driving force we have discussed. Driving force is given by, this is the activation barrier, and this driving force can be represented by delta G B as LV delta T by Tm. So LV is the latent heat of transformation, Tm is the melting point, delta T is the undercooling. Delta T is nothing but delta T is Tm minus T. I am not considering the different symbols. Of course, you have to take care of the symbols. So it's very easy. So when we say the force will be positive, but if you take these things, if you take care of these things properly, then it is okay. So let us now let us try to analyze these things. So this is what we have discussed about the. This is how the nucleation, the energy barrier. So you should remember these few things. There is a critical size, there is a critical free energy. This free energy of formation, critical free energy, that is called the activation barrier. Because you have to overcome this energy, then only the cluster can reduce the total energy by increasing the size as you go this side. So this is called the activation barrier. Delta Gv is the driving force. So this is the change in energy the system wants in free energy to become a stable state. So these few things you should not forget. Now let us if you see this equation, so this is delta G is minus Gv. So if you see this equation, this is these terms. 4 pi r square gamma SL. This provides the resistance towards nucleation. This is the term which provides resistance towards the nucleation because free energy change is positive. But and this term gamma SL is surface energy. This term is a property of the solid liquid interface. So you cannot change it much because this is related to the solid and liquid material, their structure and the other fundamental properties. But if you want to reduce the resistance, if you want the nucleation to occur easily, what will happen? You have to drop this free energy. This free energy change has to be negative. The change has to be negative. That means if system is moving from G1 to G2, G2 has to be less than G1. The free energy after transformation. This is the free energy and this is the before transformation. And so what you can do, you have to reduce this term, the resistance. So if you want to reduce the resistance term, that is nothing but like if you draw this part, it's like they are bringing it down, something like this. You can bring it down by taking the other thing constant also. So if you want to bring it down, you have to, that means earlier this was the surface energy contribution, now you have to reduce the surface energy contribution. So if you want to reduce the surface energy contribution, how can you do that? If you want to now reduce these terms, how can you reduce it? The objective is that we want to reduce this term. want to make it negative. So this term has to be reduced. That is this term. For doing that, what can we do? Because if you can reduce this resistance towards this formation is dropping, nucleation will be easier. This is done by introducing, say if this is the liquid. So if you introduce some surface, say introduce a surface where the nucleation can occur very easily. So let us draw it here. This is done by introducing some surface which helps in nucleating the solid phase into the liquid. So this kind of nucleation is called heterogeneous nucleation. So for heterogeneous nucleation, what you have to do, actually, if you see, now if you draw the energy balance, this is one energy, say, this is the solid which is being formed. This is the solid which is being formed in the, we consider this solid surface to be mold. This is like, our objective is to reduce this term, this whole contribution to the free energy, contribution by the surface energy. Now, how we are doing it? We are introducing something in the liquid which helps in nucleation. These are called nucleation site. We are introducing some nucleation site in the liquid. So this nucleation site we can consider this a small mold, or sometimes this can be the surface of the mold itself, where say for example you do the casting. So now when you have this mold, what will happen? Suppose on the mold surface one spherical cap is nucleated from the liquid. So you have the liquid here, surrounding all you have the liquid, you have the solid phase, and this is the mold. So here you have one gamma surface energy related to the solid and liquid interface. Solid and liquid interface. There you can consider another surface energy which is liquid and mold. There you have another gamma solid and mold. And this angle here, this is this angle we call theta. So theta is called the weighting angle. So now if you write the force balance equation, you can simply say that gamma Ln minus gamma Sl equal to gamma Sl cos theta. So now this gamma Sl this gamma Sl cos theta. Okay, we have written. So anyway, now how can you write the free energy change? Now the free energy change delta G here. We are not going into the full detail. We have done this thing in the last class. So I am just writing down the last equation that we got. Delta G star, that is the energy of formation, will be minus volume of the cap that is being formed, then delta G V plus gamma Sl, this is the surface being formed, A Sl plus gamma, you have another surface between solid and the mold, gamma Sl A Sl, and then if you consider this surface solid and mold is being formed by replacing the liquid and mold interface. So we have to subtract this much of energy, which is gamma liquid and mold surface energy, but the area is this area. It is same as the area of the solid and mold. So this is the contributor. This is the free energy change. this is the energy of formation in case of heterogeneous nucleation. So heterogeneous nucleation is in presence of some nucleation site. See, it can be mole boundary. Actually, in casting, the nucleation site is very often the dendrites. That there is something called inoculation. This inoculation, what is done? The dendrites which are being formed, these are broken into small parts. Now those solid particles which are free from any oxides because these are inside the liquid, those serve the purpose of nucleation site. So similar this inoculation, you can read the reference book that we follow. You can find in more details what is this. So anyway, this is the free energy of formation of this solid cap. Now V is the volume. So volume of the cap. Now it can be further reduced into minus V delta G V. This is molar quantity, volume into molar Fahrenheit change. Then plus gamma SL into A SL. This and this term ASM we can take it out. This minus this we can write it from here. So it is like minus gamma SL in SM then cos theta. So this is the free energy. So now if we call it free energy change heterogeneous. So delta G heterogeneous is similar to delta G homogeneous. We don't write it equal, we call it is similar, equivalent to delta G homogeneous, but there is some additional term which is gamma Sm A Sm then cos theta. So you see this is a negative term. So you need this much of less energy to form a solid nuclei in presence of a substrate which facilitates the nucleation. So that is the benefit that we get in heterogeneous nucleation over homogeneous nucleation. So now if you plot the free energy delta G versus R, say this is the homogeneous nucleation. Heterogeneous nucleation will be something less. Actually what happens, this delta G star, this is say homogeneous, this is the critical value and this is the delta G star for heterogeneous. Because this is heterogeneous, it is always less, so the critical value will also be less. But very interesting is this critical radius of the cluster, it remains almost same. In some textbook you can find it to be a function of some weighting angle also. But here for simplicity we are not considering these things, we are just considering it to be same. This is how we have discussed. So this is for heterogeneous nucleation, this is for homogeneous nucleation. Now let us just write down if you want to find out these critical values of R star and critical values of, what is the critical value of R star, how will you find it out? If you know the value of G, you can take a derivative of G, d delta G versus dr. If you get it into 0, then you will get the values of R star. Now if you put the values of R star that you get from here back into this delta G term, you will get delta G star also, both for homogeneous as well as for heterogeneous nucleation. So I am just writing down the equations, homogeneous nucleation and heterogeneous nucleation. So for homogeneous nucleation, this R star is given by 2 gamma SL by, you can try to do this, we have already written this equation, we have already done these things later in the class. Just for the sake of a smooth continuation of the lecture, the video lectures, I am still making this again, all this. doing all this derivation, but in very brief. So R star, what we get for homogeneous nucleation is 2 gamma SL by delta G V. This is the driving force, molar driving force, and this is the resistance. So critical size, if your molar driving force is high, critical size is smaller. And how molar driving force will be high? Molar driving force, we can write it in 2 gamma SL by, it will be Tm divided by LV into delta T. So if you want to increase this, in order to reduce the R star, you have to increase delta T. Increase delta T means delta T is Tm minus T. Tm is a constant metric property, so it has to drop. You have to go for higher undercooling. Your temperature of transformation has to be very low. Then it is possible. So that is why, say if you do casting, the moment you put the liquid material in the mold, initially the temperature is very low. The mold temperature will be of that of the room temperature. So what happens, the moment you pour it, it is experiencing a very high undercooling. Compared to the melting point, the 25 degree or 27 is quite low. So critical size will be very small. And you see in casting, you see that around the surface, you get very fine grains. Very fine grains. This is the reason, because critical size is very small. Now similarly, for homogeneous nucleation, what is delta G star? Delta G star is given by 16 pi by 3 gamma SL Q by delta GV square. So delta GV square, this is again the driving force. So as you can see, and this is proportional to 1 by delta GV. This is proportional to 1 by delta GV square. So this is actually more dependent. If you write it again in terms of the undercooling, 3 gamma SL U, then we can write it Tm square, because delta GV is, some earlier we have written delta GV is actually LV delta T by T. So just replacing this here. Then we get Tm by LV square delta T square. So now you see this quantity delta G is more dependent on temperature. So if you go for undercooling, the activation energy also reduces more faster compared to the critical size. So you can essentially nucleation rate will also be very high. Large number of nucleation of very smaller size will be formed because of the lower value of delta G, because it is proportional to 1 by delta T square, where it is 1 by T. So this you should remember. So now for heterogeneous nucleation, these values R star remains almost same, 2 gamma SL by delta GV, that is 2 gamma SL by Tm by LV delta T. However, if we see for heterogeneous nucleation, delta G star, heterogeneous, here we can call it homogeneous. So it is almost similar, gamma SL cube by delta GV square, but there is a factor of weighting, because this we have already said that in presence of some nucleation site, that is we consider it to be a mold on which, or the substrate, or a substrate over which the nucleation happens. So what is the angle? This angle is so this is the surface. So this angle is the working, this theta. So we can further write it down like this, 16 pi by 3 gamma SL0 Tn square by Lb square delta T square into f theta. So f theta is given as like just writing down the equation. F theta will be given as 2 plus, remember we are considering this, writing here 2 plus cos theta into 1 minus cos theta square by 4. And this f theta varies in between 0 to 1. If theta decreases, f theta also decreases. So that means if the Whiting angle is very low, so these are the two cases. Here it is very low, say theta 1, so this is theta 2. You can consider another situation like this, say theta 3. If the Whiting angle decreases, this f theta will decrease and delta G, this factor, multiplication factor will be very small. And then delta G star heterogeneous will be very small compared to the homogeneous nucleation. That is what is actually plotted here. But the radius size remains almost same. So, I hope you have understood this. So we'll stop it here. The next we will continue from this part what we have discussed, keeping things very easy for you.